Hey guys, Jake here coming at you with another math lesson today. Today we're going to continue discussing the topics from my recent book, The Elite Guide to AP Calculus AB. If you want to go get yourself a copy of that, you can go scan the QR code up in the corner of your screen or check the link down in the description or pinned comment below. But today we're going to continue our discussion of advanced differentiation techniques by discussing related rates. So you can see I've already got a couple things up here on the screen. We're going to go ahead and dive into an example. The other thing that I do have here is kind of my general blueprint, step-by-step process that you want to think about for related rates problems. So just to very, very quickly touch on these steps, there's kind of four main steps that you're going to go through with any related rates problem. You always want to start with drawing your diagram. It's really going to help with figuring out what sorts of shapes and quantities or distance measurements you're dealing with, and to help you create an equation, which is obviously going to be the second step. This diagram is really going to help you with creating that equation so that you can properly, proceed through the problem from there. So then you're going to, like I said, create your equation. Then you're going to take the derivative or implicitly differentiate that equation that you come up with in the second step. And then from there, you're going to solve for your desired rate of change. So I want to kind of show you an example of working through this. And I put these steps here just so we could kind of use this as a guide as we work through this problem. So the problem we're going to be doing is, let's say you're making a special latte and pouring steamed milk into a cone-shaped cup at a rate of 2.5 cubic inches per minute. The cup, with its point down, has a height of 4 inches and a base diameter of 3 inches. How quickly is the milk level rising when the milk reaches a depth of 2 inches? So, like it says in these steps, we always want to start with a diagram. So let's go ahead and start by drawing the situation that is being described here. The other thing I think is really nice about drawing a diagram first is typically these related rates problems are going to be word problems. They're going to describe a bunch of stuff that's happening in words, and drawing the diagram can really help you with kind of converting a word problem into actual math that you can work on from there. So let's first think about what sort of shape we're dealing with here. You can see right here it says we're pouring milk into a cone-shaped cup, and the cup has its point down. So that kind of tells us right there we have a cone with the point down, so something sort of like this. I'm just going to draw a two-dimensional view of this cone, looking at it directly from the side. But obviously you could imagine a cone is going to have kind of this opening up top, and it's going to get narrow down here at the point. But like I said, let's just draw kind of the side view as if we're looking at this cup, which is being held up in front of us, and we're looking at the side of it. So it would look something like that. That's kind of the general shape of the cup. Now, what we also have is we're pouring milk into this cup. So some sort of liquid is being poured into the cup. And so, as you could imagine, the level of liquid inside the cup would slowly be rising, be filling up as time passes. We don't really need to worry too much about kind of, drawing this over time necessarily. Typically, your drawing with a related rates problem is just going to be taking kind of a snapshot of a specific moment in time, which is typically going to be described within the word problem. So you can see, first of all, the liquid is being poured in at 2.5 cubic inches per minute. So this liquid is going in at a rate of 2.5 cubic inches per minute, going into the cup at that rate. And we have a cup the cup has a height of 4 inches and a base diameter of 3 inches. So we have basically this base diameter is this distance up here, the top of the cup is 3 inches, and the height of the cup is 4 inches. Okay? And what it's asking is how quickly is the milk level rising when the milk reaches a depth of 2 inches. So if the milk is 2 inches deep, that's basically halfway up the cup. So when the milk is about halfway up the cup, or I should say exactly halfway up the cup, the milk is 2 inches deep. And it's asking how quickly is this milk level rising. So basically what we're looking for is how quickly this line right here is moving up. at this moment when the milk is 2 inches deep. So that's kind of our drawing. This should give us a pretty good idea of what the situation is and how we can move on to the second step of creating an equation. So typically your equation is going to be some sort of equation that connects, like it says here, the relevant quantities such as volume, area, or distance based on the information provided. In this case, we are given that we are dealing with a cone-shaped cup, and therefore, if we're pouring some sort of liquid into a cone-shaped cup, presumably the liquid is going to fill that volume, the cone-shaped cup, and it itself will also be cone-shaped liquid. That's obviously, what happens when you pour milk into a cup. It takes on the shape of whatever the cup is. So we know that we have, what we're really looking at here is we're looking at how quickly the height of this little milk cone, how quickly this height is increasing. That's basically what we're looking at. What we're looking at is this part of the cone right here. Not necessarily the whole cup. The whole cup is not changing. It's just a cup. But the milk in it is changing over time. So that's going to be kind of the quantity that we want to look at. So we have a cone-shaped milk, basically. And we know that the volume of the milk is increasing at a certain rate, which is given 2.5 cubic inches per minute. So we have some information about the volume of this cone-shaped milk. So presumably what we probably want to start with is the equation for the volume of a cone. So let's start there and see kind of where we can go from there. So the volume of a cone, V equals 1/3 pi r squared h, where h is the height of the cone, r is the radius of the base of the cone, and then obviously 1/3 pi is just a constant there. So this is the equation in general for the volume of any cone based on a given radius and a given height. Now the challenge here, or I guess kind of the problem with just using this as our equation and kind of moving on, is we have 3 unknown variables in here. The volume is a variable, right? The volume of the milk is changing. We do know the rate at which the volume is increasing, but we don't necessarily know, or I should say, the volume is changing, which therefore makes it a variable, right? Anything as you kind of consider your situation that's being described, any quantity, volume, distance, anything like that, which changes as time goes on based on the situation described, you want to make sure you're keeping it as a variable. We don't want to be plugging anything in at this stage because the volume of this cone, this milk cone, is changing over time. As the milk level rises, the radius of the base of that milk cone is changing over time, and so is the height of that milk cone. So basically, V, R, and H are all variables. It would be incorrect to put some quantity in for those at this point because all 3 of them are changing as time goes on. So do be very careful about that. There are certain situations where you do your drawing and set up your equation, and there's certain quantities in there that aren't changing over time based on the situation being described. For those, it's okay to plug in a number because they are constant. They are not changing over time. In this case, all 3 of these quantities, V, R, and H, they do change over time because the level of the milk is increasing over time. So the problem is we typically want to get this into some sort of a situation where we just have 2 variables. Typically that's going to be our best kind of case situation there. I don't want to say that that's kind of a blanket truth of all related rates problems, but if you can do that, it's usually going to make your life a little bit easier down the road. So the kind of question is there any sort of relationship that we can figure out between any of these 2 variables so that we can kind of reduce this to a fewer amount of variables? And the answer there is yes, there is. Let's look over at this cone again real quick. We know that the milk is essentially creating a similar triangle to the overall cup. No matter what level the milk is at, it's always going to be a similar triangle, right? Like if your milk is way down here, the ratio between the height of that cone and the diameter of its base is going to be the same as the ratio of the height of the cup and the diameter of its base. Or in other words, if you look at any no matter what level you fill the milk up to, the diameter of the base of the milk is always going to be 3/4, because the ratio of the overall cup is 3/4. If you look at the diameter of the base compared to the height of the cup, it's 3/4 of the distance. So therefore that same ratio will hold true for the diameter of the milk to the height of the milk. So at this instant we are looking at, where the milk is 2 inches deep, we know the diameter of the milk cone is going to be 3/4 of 2 inches. So we can kind of say essentially that the diameter is going to be 3/4 of 2, which would come out to 3/2, right? 1.5 inches. But what that allows us to do, knowing that the diameter is going to be 3/4 of the height, we can say that the diameter in general of this milk cone, whatever level it's at, is going to be 3/4 of the height. Well, in this case we have radius. That's okay, because diameter is always just 2 times the radius, right? So if we know diameter is 3/4 of the height, that means 2 times the radius is 3/4 of the height. So we can basically take this equation, solve it for either r or h, and plug that into this volume equation to reduce it to one fewer variable, or have only one variable over here, one variable over here. So let's just go ahead and solve this for r. Basically we can just divide the 2 over to that side. We would get r equals 3/8 times h. So if we know r is always going to be 3/8 h, we can plug that in for r over here. And doing that is going to give us volume equals 1/3 pi times 3/8h all squared times h. So now this is going to be the equation that we're going to be able to go with. And of course we could simplify this further, essentially squaring 3/8, combining that with our 1/3 coefficient out here. Essentially if we do all that, we're going to end up with 3/64 pi h cubed. So we know volume equals 3/64 pi h cubed for this specific kind of ratio of cone height and diameter, or height and radius. So now that we've got our equation, we're going to go ahead and do the implicit differentiation step. Basically take the derivative of both sides of this equation, v and this side over here, with respect to time. You're always going to be doing this step with respect to time. So if we take the derivative of v with respect to time, that is simply going to give us dv dt. We don't know what v is as a function of time, so therefore the derivative of volume with respect to time is really the best we can do, which is just what dv dt represents. Then to take the derivative of the right side of our equation, we would just use power rule here. So bring the 3 down in front, lower the power by 1, and then we also have to apply chain rule. I kind of went into a bit more detail about this in my implicit differentiation video. If you want to check that out, I'll put an info card up at the top there. But bringing the power down in front, lowering the power by 1 would essentially leave us with 9/64 pi h squared times dh dt. So that's our implicit differentiation step. Now we essentially just need to solve for the desired rate. So in this case, the desired rate, what is the problem asking us to find? It is asking how quickly the milk level is rising at this moment. So again, that was this basically top of the milk, how fast is it going up? Well, that's essentially just saying how fast is the height of this milk cone increasing, right? Because we know the kind of tippy top, which is actually the bottom of our cone is fixed, and therefore the rate at which the height is increasing is just going to tell us the rate at which the milk level is rising. So those are the same thing. So finding dh dt is essentially what we're looking for here. So in order to solve for dh dt, we're going to need to plug in some height, and we're going to need to plug in some dv dt, which is how quickly the volume is increasing over time. So it's basically going to require us to plug in the rate of change of the volume, which was given. It's 2.5 cubic inches per minute. So we could plug in 2.5 for the volume. We need to plug in the height, And remember, it basically wanted us to look at the moment when the height of the milk, or the depth of the milk, was 2 inches. So we'll plug in 2 for each. And then we have the dH dt, which is the thing that we're trying to solve for. So now we could essentially just divide all of this over to the other side of the equation, and that would tell us that dH dt would essentially be 2.5 divided by all of this, right? 9 divided by 64, pi times 2 squared, which is 4. Plugging all that into a calculator would essentially just give us roughly 1.415 inches per minute. And we know our units are going to be inches per minute because all of the time measurements given in this problem were all in minutes, right? It's going increasing at cubic inches per minute. And then all of the distance measurements were all in inches. We know that the rate of change of height is essentially the units should just be whatever the units of the height are divided by whatever the units of the time are. So in this case, inches per minute. So 1.415 inches per minute is going to be your final answer there. So I hope you found this video helpful. If you did, do me a huge favor, hit that like button and go check out my book, The Elite Guide to AP Calculus AB. You can scan that QR code or go check the link in the description below. And be sure to subscribe. We're going to keep going through more problems and more topics coming up on the AP test for the next several weeks and months. So be sure to check back for more. Thanks, and see you next time.